X is a linear space over K. If you're not used to hearing linear spaces, then get ready to hear it some more, because in functional analysis, that's all you're going to hear about. Linear spaces are basically vector spaces, but a generalized version. They're over fields such as real numbers or complex numbers to a concept called an inner product, and that is basically a mapping from a linear space with itself to like an output that's in K. And if you remember, K is either real numbers or complex numbers. So we get one output from that composition, that operation. Now we have some rules that inner products have to follow. And those rules are basically very simple to understand. If you have an inner product of X with itself, then it must be non-negative. It has to be positive in a sense, or at least greater than or equal to 0. And if it is 0, then it means that X has to be 0. Now that's pretty simple to understand. If you multiply anything with 0, one of the things has had to be 0. And the third part is basically showing us that if you have an inner product operation with two scalars, meaning any two numbers, not vectors, and you multiply them, then they're also associative, meaning that they affect the other component in the inner product operation. If you have a linear space X and you have the composition of the inner product, then we can call X and that composition an inner product space over K. And once we can do that, we can perform really cool properties. One of the cool things is that now that you have an inner product on X, you can induce a norm. Remember, a norm from before was a way of measuring a magnitude or distance of a vector or an object. Now we have an inner product, and we remember an inner product multiplies things component-wise with itself. So we can get basically a distance. Now when you have a norm induced by an inner product, you can use this parallelogram identity, which basically means that the norm of x plus y squared plus the norm of x minus y squared is equal to 2 times the norm of x squared plus the norm of y squared. We're going to use this coming up in a question, which means it's question time, right? So you have a linear space X with norm, and it is strictly convex if the following condition holds. The norm of X equals the norm of Y, which equals 1, and X is not equal to Y. This implies that the norm of X plus Y is less than 2. Prove that any inner product space is strictly convex. Now, let's assume, first of all, I know you must be wondering how can norm of X and Y both equal 1 and X not equal Y? Well, imagine you have a unit circle, basically a circle around a graph, and you can basically have 2 points, X or Y, and they can both be 1, and like, for example, 1, 0 and 0, 1, and they can both have magnitude 1, because if you take the inner product of either of them with each other and take the square of it, it will equal 1. Now, back to the question. If X is an inner product space, then we can clearly use the parallelogram identity because we have a norm. So we assume X, the norm of X and the norm of Y is equal to 1, and X is not equal to Y. Then we apply the parallelogram identity, which means that the norm of X plus Y squared is equal to 2 times the norm of X squared plus the norm of, which is 2 times the norm of X squared plus the norm of Y squared minus the norm of X minus Y squared. So we rearranged some things. We took the norm of X minus Y squared and put it on the other side, on the right hand side of the equation, rearranging things in the parallelogram identity. Now we know that norm of X and Y are both 1, so we sub it in and we can basically do a few computations, and we get the norm of X plus Y squared is 4 minus the norm of X minus Y squared. I missed a square at the end, but on the norm of X minus Y, but it's supposed to be there. Now, because X is not equal to Y, we have the norm of X minus Y squared must be greater than 0. Now, this means that we clearly have an inequality, actually, if we remove the norm of X minus Y squared from the equation. If we remove it from the equation that we had before, then we can easily say that the norm of X plus Y squared is less than 4. Because if you remove the norm of X minus Y squared from the right-hand side, you'd no longer have an equality, but instead you have an inequality, which means that the right-hand side is greater than the left-hand side. Now, if you take the square root of both sides, then you get the norm of X plus Y squared is less than 2, which is what we had to prove. So what do? we showed that we showed that if we have an inner product in a linear space X, then we can use the parallelogram identity. And given the conditions of X and Y both having the normal 1, we showed that it is a strictly convex. Now here's what a graphical representation of strictly convex in this case would look.